Hello there, and welcome to the Sleepy Science Channel. Tonight, we're drifting into one of the strangest and most overlooked wonders in the universe, cosmic dust. It may sound small, it may even sound unimportant, but this fine material has been gently shaping the universe since time began. It builds planets and stars, traverses intergalactic space, and even carries the remains of ancient lost worlds. Some of it is older than Earth. Some of it was forged in stars that died long before our sun was born. And some of it is falling through our sky right now, settling so softly that no one notices. Cosmic dust fills space with motion, history, and possibility. It gathers in glowing clouds and vibrant disks. It streams from comets, drifts between planets, and preserves the memory of ancient stellar explosions. In something so tiny, the universe has stored an astonishing story. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is get settled in. Let your shoulders soften. Let your breathing slow, and allow your mind to settle into stillness as we embark on this fascinating journey through the cosmos together. Let's begin. Cosmic dust is older than Earth, and some of it is stardust. Long before Earth existed, before the oceans formed, before the moon was torn from young rock, tiny mineral grains were already drifting through the galaxy. Some were forged inside ancient red giant stars. Others were blasted outward when massive stars exploded. Those grains crossed interstellar space, survived the birth of our solar system, and became trapped inside primitive meteorites. Scientists have found them in the lab and confirmed their age from their unusual atomic fingerprints. That means a few dust grains in our collection cabinets are literally older than our planet. They are not just old matter. They are surviving pieces of stars that lived and died before the sun ever shone. It is astonishing to think that something smaller than a speck of smoke can outlast worlds. In cosmic dust, the universe keeps relics from a time before Earth had a sky, a sea, or even a name. Every night, Earth is showered by tons of cosmic dust. While most people sleep, our planet keeps moving through a fine, invisible rain from space. Tiny particles sweep into the atmosphere at enormous speed. Most are so small that they never become dramatic shooting stars. Instead, they heat up, soften, and settle downward as microscopic spherules or mineral fragments. This happens constantly, not as a rare event, but as part of ordinary life on Earth. Dust from asteroids, old comets, and shattered debris enters the air above every ocean, desert, and city. It lands on rooftops, in snowfields, on quiet roads, and across the open sea. You could be standing outside beneath a clear night sky and never realize that material from space is passing over you in huge numbers. It sounds unbelievable, yet Earth quietly collects this extraterrestrial drizzle all the time. The planet is not sealed off from the cosmos. It is being touched by it every single night. The faint zodiacal glow is sunlight shining off drifting dust. There is a ghostly pyramid of light that sometimes rises from the horizon after sunset or before dawn. It is soft, pale, and easy to miss. Many people assume it is leftover twilight. It is not. That glow comes from countless tiny dust grains spread through the inner solar system, each one catching and scattering sunlight. Together they create a luminous haze that stretches along the plane where the planets travel. Seen from a dark place, it can look almost unreal, like a secret lantern hidden in the sky. What makes it so beautiful is its source. This is not a nebula around a distant star or a galaxy millions of light years away. It is dust in our own celestial neighborhood, shining because sunlight is bouncing off drifting debris between worlds. The next time someone says dust is dull, it is worth remembering that dust can paint one of the sky's most delicate and mysterious displays. Much of your body was forged in stars, then scattered as dust. The calcium in your bones, the iron in your blood, the oxygen you breathe, and the carbon that helps build every living cell were not made on Earth. They were created in stars. Light elements emerged early in cosmic history, but many of the atoms that matter most to life were forged later in stellar cores and violent explosions. When those stars aged, swelled, or died, they released newly made elements into space. Some drifted outward as gas and dust, mixing into giant clouds that would one day give birth to new stars and planets. Our sun formed from one of those enriched clouds. Earth formed with it. So did everything on it, including you. This is not a poetic metaphor dressed up as science. It is a physical history written into every atom in your body. You are built from material that passed through stars, wandered as cosmic dust, and eventually became alive enough to wonder where it came from. Some cosmic dust grains formed before our sun was born. Inside certain meteorites, scientists have discovered tiny grains with isotopic patterns so strange that they cannot have formed in our solar system. Their atomic ratios point instead to ancient stellar furnaces that existed before the sun. These grains are called presolar because they predate the cloud that collapsed to form our star and its planets. In a sense, they are survivors of a lost galaxy, preserved through one of the most chaotic events imaginable, the birth of a planetary system. During that process, most older material was melted, mixed, or destroyed. Yet a few grains endured. Locked inside primitive rock, they waited for billions of years, until human beings split the meteorites apart and recognized what they were holding. That is an extraordinary moment in science. It means we can examine matter that took shape before sunrise existed as an idea in this corner of space. Some dust is not merely ancient. It is older than our entire local story. Space between stars is not empty. It is filled with dust. When people imagine the space between stars, they often picture perfect emptiness. In reality, the galaxy is threaded with vast clouds of gas and dust. These regions can be so cold and dark that visible light struggles to pass through them. Dust grains there are tiny, but their collective presence matters enormously. They dim starlight, redden distant stars, and create dark lanes across the Milky Way that are visible even in ordinary sky photographs. In denser clouds, the view becomes stranger still. Regions that look like black holes in the star field are often not empty at all. They are places where dust is blocking the light behind them. So the darkness itself is a clue that matter is there. It is a wonderful reversal. What looks like absence is often presence. The galaxy is not a bare hall filled with isolated suns. It is a textured, dusty place, layered with veils, shadows, and hidden structure. Dust can hide newborn stars, then help new planets appear. In stellar nurseries, gravity gathers gas and dust into cold, dense knots. As one of these knots collapses, the center heats up, and a young star begins to form. At first, it is deeply buried. Thick dust blocks the visible light, which is why many newborn stars remain hidden from ordinary telescopes. Yet the same dust that conceals them also becomes part of what comes next. Around the infant star, leftover material settles into a rotating disk. Within that disk, dust grains collide, cling, and grow. The process begins on the tiniest scale imaginable. Little particles brush together, stick through delicate forces, and slowly build larger aggregates. Given enough time, those clumps can become pebbles, planetesimals, and eventually worlds. So dust plays a double role in one of the grandest transformations in nature. It first draws a curtain around stellar birth. Then, behind that curtain, it becomes the raw material from which entirely new planetary systems can emerge. Tiny dust grains helped build worlds, moons, comets, and asteroids. It is easy to think planets must begin with something dramatic, a giant glowing sphere or a great slab of rock. The real beginning is far smaller. In the early solar system, a disk of gas and fine solid particles circled the young sun. Within that disk, dust grains started the long climb toward complexity. They bumped, stuck, and built fragile clumps. Those clumps grew into pebbles, then into larger bodies whose gravity helped them gather more material. Over immense stretches of time, this upward cascade produced the first building blocks of planets. Some became rocky worlds. Some remained as asteroids. Some stayed icy and became comet nuclei. Others joined growing planets and were shaped into moons. The scale of the final result makes the starting point feel almost absurd. Mountains, craters, oceans basins, and frozen comet hearts all trace their ancestry back to dust grains so small they could drift on a breath. Entire worlds began as a problem in fine powder. Dust from comets can paint meteor showers across Earth's sky. A meteor shower begins long before any streak of light appears overhead. As a comet travels around the sun, heat loosens gas and embedded dust from its surface. That material spreads out along the comet's orbit, leaving a long stream of debris in space. If Earth later passes through that stream, the tiny particles slam into our atmosphere at tremendous speed. They glow for a moment and carve bright lines across the night. Seen one by one, they are simple flashes. Seen together, they become one of the sky's most beloved spectacles. The Perseids, Leonids, and Geminids all connect us to old trails of orbital debris. That idea has a special kind of wonder. A meteor shower is not random weather. It is Earth moving through the dusty remains of a small wandering body that has been circling the sun for ages. What looks like a shower of stars is really a comet writing its path across our atmosphere. Even now, alien dust from beyond our solar system passes through. Our solar system is not isolated from the wider galaxy. As the sun moves through interstellar space, tiny grains from beyond our planetary neighborhood can drift inward. Some are pushed and sorted by solar radiation and a solar wind. Others keep coming, crossing the paths of planets like faint messengers from outside. Spacecraft have detected this incoming interstellar dust and measured its motion, showing that not every grain near Earth was born from local comets or asteroid collisions. That means truly foreign material is passing through our system right now. It comes from regions shaped by other stars, other clouds, and other histories. These grains are microscopic, yet the idea is immense. Matter from the galaxy beyond us does not stop at some invisible border. It enters, flows through, and leaves traces that instruments can find. In a very real sense, the solar system has open doors. Even now, it is being visited by dust that began its journey under another sky. Dust can be smaller than smoke, yet shape entire galaxies. A single grain can be so tiny that millions could drift unnoticed through a sunbeam, and yet enormous regions of a galaxy answer to its presence. Dust dims starlight, redirects heat, and changes how gas cools and collapses. That means it can influence where stars appear, how bright whole regions look, and what astronomers think they are seeing when they study distant systems. In spiral galaxies, dust helps carve out dark bands and glowing arms, giving structure to scenes that might otherwise look smoother and simpler. It also helps create the conditions that allow new stars to emerge from cold clouds. Remove enough dust, and a galaxy would not just lose some decoration. It would behave differently. Its light would travel differently. Its future would shift. That is part of what makes the subject so astonishing. The universe is shaped not only by colossal masses and violent explosions, but also by powder fine enough to ride a breath. Some dust grains are fragile glass, born in ancient stellar fire. Not all cosmic dust is rugged stone. Some grains began as droplets of molten material in the outflow from dying stars, then cooled into tiny glassy particles while racing through space. Imagine a red giant swelling outward and shedding its outer layers into the dark. In that expanding flow, atoms met, bonded, and froze into microscopic solids. Some became silicate grains with the chemistry of minerals we know on Earth. Others remained partly disordered, more like glass than crystal, because they cooled too quickly for a neat internal pattern to form. That history matters, because their very texture records the conditions of a vanished star. These grains are delicate travelers. They can be altered by shocks, radiation, and heating, yet some still survive long enough to be locked into meteorites or drift through interstellar clouds. A tiny glass grain may look unremarkable under a microscope, but it was once part of a stellar wind pouring off a giant sun. Other grains are tiny crystals that survived impossible cosmic journeys. Some particles are not glassy and shapeless at all. They are beautifully ordered crystals, with atoms stacked in repeating patterns that formed under precise conditions and then endured for ages. That survival is the astonishing part. A grain may be blasted from a star, drift through interstellar space, pass through turbulent clouds, enter the violent region where a young solar system is assembling, and still remain intact enough for scientists to study. Its structure today. Certain minerals, such as silicon carbide and tiny crystals rich in oxygen-bearing compounds, preserve clues about the stars that forged them. Their atomic order becomes a kind of resilience. They are small, but they are not flimsy. They are time capsules with geometry. To think that a crystal smaller than dust on a bookshelf can cross light years, outlast stellar death, and survive the birth of planets is to realize how durable matter can be when the universe arranges it just right. Dust clouds can make bright stars vanish from our view. A star can be blazing with enormous power and still disappear behind a curtain of dust. That is one of the strangest tricks in astronomy. The star itself does not go out. The light is simply blocked, scattered, and absorbed by clouds between us and the source. In some parts of the sky, this effect is so strong that whole regions look eerily empty, as though the stars have been erased. In truth, the missing light is telling us that dense material stands in the way. This can happen on grand scales in dark nebulae, where star fields seem bitten away, or around individual stars that flicker behind drifting dusty shells. For observers on Earth, the disappearance can feel almost supernatural. Something brilliant is there, but visible light cannot reach us cleanly. Dust turns absence into evidence. When the sky suddenly looks blank where it should be crowded, it often means a hidden cloud is standing between us and a starry world beyond. The Milky Way's dark lanes are vast rivers of light-blocking dust. On a truly dark night, the Milky Way does not appear as a smooth wash of light. It is streaked with shadow. Across that bright band run long dark lanes that split, twist, and deepen the view. Those lanes are not empty gaps between stars. They are immense concentrations of dust spread across our galaxy. Each one is made of tiny particles, but together they block enough starlight to create dramatic black channels against the glow of billions of suns. In photographs, they look almost like cracks in the sky. In reality, they are dense regions full of material that may later help form new stars and planetary systems. That is part of their beauty. The darkness is not dead space. It is loaded with possibility. When you look into one of those lanes, you are staring into a place where light is being held back by matter so fine and yet so abundant that it can redraw the appearance of the entire galactic sky. Infrared telescopes can see through dust that blinds ordinary starlight. Visible light is easily stopped by dust, which is why many regions of space look dark or impenetrable in ordinary images. Infrared light behaves differently. Its longer wavelengths can slip through dusty clouds far more effectively, allowing astronomers to peer into places that once seemed sealed off. This changes the universe completely. A black patch in visible light can become crowded with hidden stars in infrared. A dense stellar nursery can suddenly reveal glowing newborn objects, warm disks, and tangled structures inside the cloud. It is like switching from one sense to another and finding a secret city behind a wall. Telescopes built for infrared astronomy have transformed our picture of the cosmos for exactly this reason. They do not merely sharpen what we already knew. They reveal what dust was hiding. Entire generations of stars, buried clusters, and the warm glow of dust itself come into view. The dark ceases to be blank and becomes inhabited. Without dust, many of the universe's most beautiful nebulae would disappear. Some of the most famous sights in astronomy depend on dust for their drama. The pillars of creation, the Horsehead Nebula, and many glowing clouds that fill calendars and observatory walls owe much of their appearance to fine particles mixed through gas. Dust outlines structures, creates silhouettes, and shapes the contrast between bright and dark. Without it, many nebulae would lose the sculpted look that makes them feel almost architectural. There would be less shadow, less depth, and less sense of hidden chambers inside the cloud. Dust also scatters and reflects starlight in ways that can tint and soften whole regions, helping produce the luminous appearance of reflection nebulae. In other words, dust is not just part of the scenery. It is one of the great visual artists of the cosmos. It creates edges, veils, and hidden hollows. Some of the universe's most breathtaking scenes would look flatter, plainer, and far less mysterious without these tiny grains at work. Dust turns harsh starlight into a softer glow of heat. When intense starlight strikes dust, the story does not end with light simply being blocked. The grains absorb energy, warm up, and then release it again at longer wavelengths as heat. This is one of the quiet transformations that happen all over the universe. Energetic radiation from stars hits tiny particles, and those particles answer by glowing in the infrared. The result is a softer kind of light, invisible to human eyes, but rich with information. It tells astronomers where dust is being heated, how much energy a region is absorbing, and what the environment around young stars or active galaxies might be like. It is a little like sunlight warming dark ground at dusk, except on a cosmic scale. Harsh brilliance is taken in and returned as a gentler thermal glow. Dust becomes a translator, converting one kind of radiance into another. What seems like mere obstruction is actually a hidden conversation between starlight, matter, and warmth. Cold dust can shine brightest in wavelengths human eyes never see. There are regions of space that look dark and lifeless in ordinary photographs, yet they are quietly glowing with their own kind of light. Cold dust does this. Even when it is far from hot stars and chilled to astonishingly low temperatures, it still emits radiation, mostly in the far infrared and submillimeter part of the spectrum. Human eyes are blind to that glow, which means an entire layer of the universe is missing from normal sight. Specialized observatories can map it, and when they do, vast hidden structures appear. Frigid clouds, long filaments, and concentrations of material show up like ghost landscapes. In these maps, the coldest and quietest places often become some of the most important, because they are the places where gravity may soon gather matter into stars. So darkness can be deceptive. A cloud that seems absent in visible light may actually be radiant in another wavelength, shining not with fire, but with deep cosmic cold. Dust helps cool collapsing clouds, letting new stars finally ignite. For a star to form, gravity must win. A cloud has to shrink inward until its center becomes dense and hot enough for nuclear fusion to begin. That sounds simple, but there is a problem. If the cloud cannot lose heat, pressure builds and fights back against the collapse. dust helps solve that problem. Mixed through the gas, grains absorb energy and radiate it away, allowing the cloud to cool more effectively. That cooling makes further collapse possible. In a sense, dust helps open the path to ignition. It does not provide the power of the future star, but it helps create the conditions that allow the star to be born at all. This is one of the subject's most surprising roles. Dust is not merely leftover debris drifting through space. It is part of the machinery of creation. A particle smaller than anything you could feel with your fingers can help a cloud surrender to gravity and become a sun. Young stars are often born wrapped inside cocoons of dust. The birth of a star is not usually a clean or exposed event. It happens inside dense regions where gas and dust gather into thick envelopes around the growing object. These dusty cocoons hide the infant star from ordinary view and create a world of deep shadow lit mostly by heat and scattered radiation. Inside, matter continues to fall inward. Jets may burst from the poles. A disk may spin around the center. The whole scene is active, violent, and hidden at once. From the outside, astronomers may see only a faint glow in the infrared or the signature of warm dust. That secrecy is part of what makes stellar birth so compelling. One of the most important events in the universe often begins behind layers of obscuring material. The dust protects, conceals, and shapes the environment in which the star grows. It is a cradle, a curtain, and a workshop, all at the same time. Suns begin in concealment before they ever shine openly. Planetary systems begin as spinning disks of gas and dust. Around a young star, leftover material does not simply hover in chaos. It flattens into a rotating disk, broad and bright, made of gas, dust, and future possibilities. This is where planetary systems begin. Within that spinning structure, different regions can have different temperatures, chemistries, and kinds of solid material. Closer in, heat favors rock and metal. Farther out, colder conditions allow ice to join the mix. Over time, the disk becomes a place of sorting, drifting, sticking, and collision. It is less like a single event and more like a long construction era. Every familiar feature in a mature system, rocky worlds, gas giants, moons, comets, asteroid belts, can trace its origin back to this flattened, rotating nursery. When astronomers find such disks around other stars, they are seeing the opening chapter of world-making. It is extraordinary to realize that planets do not appear fully formed. They begin in luminous, dusty circles turning around a star that is itself still young. Dust grains can stick, clump, and slowly become planetesimals. The jump from dust to world is one of the great miracles of natural history, and it begins with a very humble step. Tiny particles collide at low speeds and sometimes stick instead of bouncing apart. Electrostatic forces, delicate surface effects, and the porous fluffiness of young aggregates can all help them hold together. Once small clumps form, they behave differently from single grains. They drift, collide, and collect more material, growing into pebbles and then into larger bodies. Eventually, some become planetesimals, the first truly substantial building blocks of planets. These are not yet full worlds, but they are big enough for gravity to start taking the lead. From there, growth can accelerate through collisions and accumulation. The process is messy, slow, and full of failure, yet it works. That is the part worth savoring. Mountains, moons, and continents begin not with grandeur, but with grains learning in a way to hold hands and stay together. Every rocky planet began as countless collisions between tiny dust grains. Earth feels massive and singular beneath our feet, but its first chapter was written in impacts too small for the eye to follow. In the young solar system, solid particles moved through the disk around the sun and struck one another over and over. Some shattered, some bounced, some fused. Across unimaginable numbers of encounters, dust became pebbles, pebbles became rocks, and rocks became bodies large enough to draw in more material with gravity. The eventual result was the assembly of rocky planets. That means the ground beneath every city, forest, and mountain has an ancestry in dust collisions. The idea is wonderfully disproportionate. The cliffs of a continent and the iron core of a planet are the far descendants of microscopic meetings in a cloud around a newborn star. When you think of a planet forming, it is tempting to imagine a single grand event. The truth is more patient and more astonishing. Worlds are built out of repeated little impacts until the little becomes immense. Some dust grains grew inside disks circling stars not unlike ours. When astronomers observe young sun-like stars, they often find dusty disks around them that look like early versions of what once surrounded our own sun. Inside those disks, grains are already changing. They collide, grow, and sometimes settle toward the midplane, where denser bands of material can form. In some systems, the dust shows signs of having become larger and more processed than the fine grains found in interstellar clouds. That matters because it means the first steps toward world building are not unique to our history. They're happening elsewhere, around stars with temperatures and masses similar to the one we orbit. In a very real sense, we can watch other possible solar systems in their youth. Somewhere out there, within a dusty disk around a sun-like star, material may now be moving through the same ancient stages that once led to Earth, Mars, and the asteroid belt. Cosmic dust makes planetary family resemblance visible across light years. Dust inside protoplanetary disks can gather into rings and gaps. Some of the most striking images in modern astronomy show young stars surrounded by disks marked with beautiful rings and dark gaps, almost like the grooves on a vast cosmic record. These patterns are often traced by dust. In certain regions, particles become concentrated. In others, they are depleted, pushed aside, or trapped by pressure variations in the gas. The result is structure on a grand scale, visible from immense distances. What makes these images so captivating is that they feel like snapshots of order emerging from a former haze. The disk is no longer a simple blur. It has architecture. Rings can form for several reasons, including the influence of growing planets, changes in temperature, and the way gas pressure sorts drifting grains by size. Dust becomes a tracer of hidden dynamics. It reveals that a young system is already being shaped from within. A star only just born may already be surrounded by the first signs of an organized planetary future. Those dusty rings may reveal where hidden young planets are forming. A young planet can be difficult to see directly, especially when it is still embedded in a bright disk of gas and dust. Yet its presence may still be written into the surrounding material. As a growing planet moves through the disk, its gravity can disturb the dust and gas, carving lanes, piling up rings, or creating asymmetries that observatories can detect. In that sense, a planet can announce itself before we ever see it plainly. Astronomers study these patterns almost like detectives studying footprints. A gap may hint at a body clearing its neighborhood. A lopsided clump may suggest a place where particles are being trapped. Spiral features may betray the gravitational influence of something young and hidden. Dust becomes the visible consequence of an invisible sculptor. That is one of the great thrills of the subject. We may not always catch the planet itself, but we can watch the disk react and realize that world formation is already underway. Cosmic dust helped pave the road from pebbles to planets. There is a long middle chapter in planetary creation that often gets overshadowed by the grander beginning and end. People hear about dust and then jump straight to planets, but between those stages lies an extraordinary climb through pebbles, boulders, rubble, and growing planetesimals. Dust is where that road begins. Without tiny grains forming the first clumps, there would be no pebbles to drift, no larger solids to collide, and no embryos for gravity to enlarge into worlds. In some regions, pebbles may have streamed together rapidly enough to collapse into larger bodies almost in groups, speeding the process. In others, repeated collisions slowly built upward through persistence. Dust made all of that possible. It supplied the first solids that could be sorted, concentrated, and assembled into something bigger. The path from powder to planet is not a leap. It is a staircase. Cosmic dust built the first steps, and without those steps, no rocky world would ever have had a chance to rise. The moon has no air, so cosmic dust strikes it directly. Earth has an atmosphere that burns up or slows many incoming particles, but the moon has no such shield. Dust from space reaches the lunar surface directly, striking bare ground that has been exposed for immense stretches of time. Each impact may be tiny, yet across ages the effect is relentless. The surface is constantly gardened, churned, and weathered by incoming micrometeoroids. Grains smash rock, melt little droplets, and help create the fine powder called regolith that covers much of the moon. This means the lunar soil is not just broken stone. It is a record of endless bombardment by space debris. There is something stark and beautiful about that. The moon does not merely orbit in silence. It is in direct contact with the dust of the solar system, taking hit after hit with no air, no wind, and no rain to soften the encounter. Its surface is shaped by exposure, and cosmic dust is one of the quiet sculptors. Mars is constantly dusted by particles drifting through interplanetary space. Mars is famous for its own local dust storms, but another, softer rain is always arriving from beyond the planet itself. Interplanetary particles cross Martian space and settle onto the surface or burn lightly through its thin atmosphere. Over time, this adds an extraterrestrial ingredient to a world already rich in iron-colored soil and ancient volcanic rock. Because the atmosphere of Mars is far thinner than Earth's, incoming particles interact with it differently. Some survive more easily. Some leave subtle traces in the upper air. Others join the surface record, becoming part of the layered story of the planet. It is fascinating to picture Mars not as an isolated desert, but as a place continuously touched by drifting material from the wider solar system. The red planet is being dusted from above, while its own winds move dust below. Two kinds of fine matter, one local and one cosmic, meet there. Even a seemingly barren world remains open to traffic from space. Even giant planets collect dust, though their gravity changes everything. When people picture Jupiter or Saturn, they usually imagine vast storms, thick clouds, and crushing gravity, not drifting dust. Yet dust still finds its way there. Tiny particles pass through the outer solar system from comets, collisions, and distant debris streams. And giant planets sweep up part of that material as they move. Their immense gravity changes the whole story. Instead of simply falling straight in, grains can be bent onto new paths, captured for a time, or flung away at great speed. Some become part of faint, dusty structures around the planet. Others plunge into the atmosphere and vanish in a flash of heat. In a sense, giant planets act like cosmic traffic controllers, rearranging the movement of fine material around them. They do not just collect dust. They sort it, scatter it, and sometimes imprison it in delicate rings and halos. Even something as small as drifting powder must obey when a giant world enters the scene. Saturn's rings are filled with icy particles, from boulders to dust. From far away, Saturn's rings look smooth and almost solid, like bright grooves cut around the planet. Up close, they are nothing like that. They are made of countless separate particles, most of them rich in water ice, ranging in size from large chunks down to fine dust. Some pieces are as small as grains you might brush from a sleeve. Others are as large as houses. Together they orbit in an astonishingly thin and crowded disk, each fragment following gravity, while constantly feeling the pull of nearby moons and neighboring ring material. Sunlight glints off this icy swarm and gives the rings their dazzling brightness. Yet beneath that beauty is constant motion and subtle conflict, with particles colliding, clumping, and breaking apart. The result is one of the most elegant structures in the solar system. Saturn's rings are not a single object at all. They are a vast community of icy fragments dancing together around a giant world. Enceladus sprays icy dust into space from its hidden ocean. Enceladus is a small moon, bright and frozen at the surface, yet it hides one of the most extraordinary engines in the solar system. Near its south pole, great cracks in the ice vent material outward in towering plumes. These eruptions are not smoke or volcanic ash. They are jets of water vapor, ice grains, and other material launched from a subsurface ocean that lies beneath the crust. Some of those icy particles fall back like snow. Others escape the moon's weak gravity and stream into space. That means a tiny world, barely a fraction of Earth's size, is actively feeding its surroundings with fresh dust from an ocean no one can see directly. It is a breathtaking image. A frozen moon, far from the sun, is breathing icy grains into the dark. Each drifting particle is evidence that beneath the bright shell of Enceladus, liquid water and internal energy are still at work, turning a small moon into a source of cosmic spray. That frozen spray helps feed one of Saturn's vast rings. One of Saturn's great rings is not merely leftover debris from the distant past. Part of it is being refreshed right now. The icy material blasted from Enceladus does more than rise and fall around the moon itself. A portion escapes into orbit and spreads out along the path of Saturn's E-ring, a vast and diffuse structure that stretches enormously far compared with the brighter main rings. In effect, a hidden ocean under a tiny moon is helping maintain a ring around a giant planet. That connection feels almost magical. A crack in ice on a small world sends out grains that become part of something planetary in scale. The ring is not static decoration. It is linked to an active source. Every particle added to it is part of an ongoing exchange between moon and planet. Saturn does not simply wear rings. In this case, one ring is being quietly nourished by the frozen breath of an icy satellite. Comets shed dust whenever sunlight warms their ancient frozen surfaces. A comet can spend much of its time in deep cold, dark and inactive, preserving material from the early solar system like a frozen archive. But when it swings closer to the sun, sunlight begins to warm its surface. Ice turns directly into gas, and that escaping gas can drag embedded dust away with it. Suddenly the comet becomes active. Fine particles that may have remained locked in place for billions of years are lifted off and released into space. This is one of the reasons comets are so captivating. They do not simply travel. They change character as they approach the sun, almost as if waking up. The dust they shed can range from tiny grains to larger fragments, and over repeated passages, much of the comet's surface may be reshaped by this ongoing loss. Each active comet is both ancient and temporary, revealing old material while slowly eroding itself. Sunlight does not just illuminate a comet, it helps pull its dust into the open. A comet's glowing tail is partly made of dust. The tail of a comet can look like a luminous banner unfurling across space, but it is not made of one single thing. Part of that glow comes from dust released from the nucleus as the comet warms. Sunlight scatters off those tiny particles, making the dusty tail visible across enormous distances. This is different from the bluish ion tail made of electrically charged gas, which responds strongly to the solar wind. The dust tail is usually broader, softer, and often curved. It traces the motion of particles that still remember the comet's orbit even as radiation pressure pushes them away. That is why a comet can seem to carry a glowing veil behind it, wide and graceful rather than sharp and straight. The beauty is real, but so is the material. What you are seeing is sunlight catching on grains that were once frozen into an ancient body. A comet's shining tail is partly a cloud of liberated dust made visible by the sun. Solar radiation can push tiny dust grains into long, luminous tails. Light feels weightless to us, but it carries momentum, and on tiny dust grains in space, that momentum can matter. When sunlight strikes particles released from a comet, it does not just warm them and make them glow. It also pushes on them. For larger objects, the effect is tiny, but for grains small enough, that steady pressure can reshape their paths and drive them away from the sun. Over time, vast streams of dust are stretched into long, shining tails that fan out behind the comet. This is one of those cosmic effects that feels almost impossible until you picture the scale correctly. A grain can be so small that light itself becomes a meaningful force. The result is one of the most elegant sights in astronomy, a tail built not only by release from the comet, but by sunlight physically steering the liberated particles into a broad, luminous sweep. Even light can act like wind when the grains are small enough. Some comet dust is so dark it reflects little light. It is tempting to imagine comet dust as sparkling frost or glittering powder, but much of it is nothing like that. Some of it is astonishingly dark, richer in carbon-bearing material and complex compounds that absorb more light than they reflect. This is one reason comet nuclei themselves can be surprisingly black, darker than many familiar rocks on Earth. The dust they release can carry some of that darkness with it. That fact changes the mood of the whole subject. These grains are not just pretty particles catching sunlight. Some are ancient, sooty fragments from deep time, preserving primitive material from the solar system's earliest era. They drift away from a bright tail, yet individually they may be closer to charcoal than to snow in their reflectivity. There is something wonderfully strange about that contrast. A comet can produce a glowing spectacle in the sky while shedding dust, that is, grain for grain, among the darkest material moving through our planetary neighborhood. Asteroid collisions constantly grind rock into fresh clouds of drifting dust. The asteroid belt is not a static museum of untouched relics. It is an active place where impacts still happen. When asteroids collide, they can fracture, chip, or even shatter, producing fresh dust that spreads through surrounding space. Some collisions are gentle by cosmic standards, leaving craters and ejecta. Others are catastrophic, reducing a body to fragments that continue colliding with one another and creating even more fine material. This grinding process is one of the quiet engines that keeps dust circulating through the solar system. What begins as solid rock can be turned into drifting particles through repeated violence. Entire asteroid families, made of objects sharing a common collision history, stand as evidence of these ancient breakups. In a sense, dust is one of the afterlives of impact. A fragment becomes a smaller fragment, then a smaller one still, until part of it enters the realm of powder. Even bare rock, given enough collisions, can be transformed into a cloud. Much of the zodiacal dust likely comes from comets and collisions. The soft haze that creates the zodiacal light did not appear from nowhere. It is thought to be supplied mainly by two ongoing sources. One is comets, which release dust as sunlight warms their surfaces and freeze embedded particles. The other is collisions among asteroids and smaller rocky bodies, which grind larger objects into fine debris. Together, these processes keep replenishing the inner solar system with drifting material. Without that steady supply, sunlight would have far less dust to scatter, and the zodiacal glow would fade. This is part of what makes the phenomenon so satisfying. It links a beautiful sky display to active processes happening all the time. The faint pyramid of light after sunset is not just a static feature. It is the visible consequence of comets shedding material and rocky bodies smashing one another over ages. Behind that delicate glow lies a dynamic balance between loss, renewal, and the endless production of fresh dust near the sun. Some inner solar system dust may even be linked to Mars. Mars is not only a destination for drifting dust. It may also be connected to some of the dust moving through the inner solar system. Tiny particles can be launched from planetary surfaces when impacts strike with enough force, and Mars, with its lower gravity than Earth, is more vulnerable to losing material this way. Over immense spans of time, meteoroid impacts may have blasted fine debris upward and outward, contributing a small share to the population of particles circulating through nearby space. There are also more subtle possibilities involving how Martian material gets processed and redistributed after escape. The idea is fascinating because it blurs the boundary between planet and interplanetary environment. Mars is not just sitting in space while dust passes by. It may have donated some of that dust itself. In that sense, a tiny grain drifting near the Sun might carry a history tied to an ancient impact on the red planet. Whole worlds can shed powder into space. Dust spirals slowly sunward as sunlight steals its orbital momentum. Sunlight does more than illuminate dust. Over long periods, it can subtly change the orbit of a grain and cause it to drift inward toward the Sun. The effect is gentle, but relentless. A particle moving around the Sun absorbs sunlight and then re-radiates energy in a way that slightly robs it of orbital momentum. Because of that loss, the grain can no longer maintain exactly the same path and begins to spiral inward. This does not happen dramatically. There is no sudden plunge. It is a slow surrender, measured over many orbits, as a tiny grain gradually falls closer to the central star. The idea is deeply elegant. A particle released by a comet or collision may wander through space for ages, not only under gravity, but under the subtle pressure and thermal consequences of light itself. Dust in the solar system is not simply circling passively. Some of it is being quietly nudged inward by sunlight, one orbit at a time. This slow inward drift is called the Poynting-Robertson effect. Astronomy has a gift for naming delicate cosmic processes after the people who helped explain them, and this is one of the most graceful examples. The Poynting-Robertson effect describes the slow inward drift experienced by small particles orbiting a star. It happens because the grain is moving while it absorbs incoming light and re-radiates energy. That interaction creates a tiny drag that saps orbital momentum and makes the particle spiral sunward over time. What makes this so fascinating is how far it is from ordinary intuition. We think of light as revealing objects, not breaking them. Yet for dust, light becomes part of the machinery that reshapes orbits. The effect helps explain why small grains do not remain in the same place forever, and why the inner solar system needs continual replenishment of dust from comets and collisions. Without that supply, the Sun would slowly clear some of the fine material away. Even dust can feel the long hand of starlight altering its destiny. Tiny dust grains can become electrically charged by sunlight and plasma. In space, a dust grain is not always just a neutral speck of matter. Sunlight can knock electrons from its surface, and surrounding plasma can add or remove charged particles as well. The result is that many grains develop electric charge. Once that happens, their behavior can become far more interesting. They still respond to gravity, of course, but now, electromagnetic forces can start to matter too. Around planets, moons, and near the Sun, this can alter how grains move, where they collect, and whether they cling to surfaces or leap away from them. It is a beautiful reminder that space is not empty and quiet in the simple way people imagine. It is full of radiation, charged particles, and subtle interactions that can transform the fate of something microscopic. A dust grain under sunlight is not merely warmed and illuminated. It can become part of an electrical environment, carrying charge and entering a new kind of cosmic behavior altogether. Charged dust can behave strangely near planets, moons, and the Sun. Once a dust grain carries electric charge, gravity is no longer the whole story. In regions filled with magnetic fields and plasma, charged particles can move in ways that seem almost uncanny. They may be lofted, trapped, deflected, or sorted by forces that do not matter much for larger objects. near planets with powerful magnetospheres, around airless moons exposed to solar radiation, and in the electrically active environment close to the Sun, dust can follow paths that would make little sense if gravity alone were acting. Scientists have observed hints of dusty streams, strange transport, and charged behavior that reveal how dynamic these environments really are. This is one of the reasons cosmic dust stays so fascinating. The grains are small enough to become sensitive to a whole extra layer of physics. They do not always fall, orbit, or drift in the ways intuition expects. Sometimes they behave more like participants in a hidden electrical weather system than like ordinary specks of matter. Dust can levitate above airless worlds under electric forces alone. On worlds without a substantial atmosphere, the boundary between ground and space can become electrically active in surprising ways. Sunlight charges exposed surfaces, shadowed regions behave differently, and fine dust can respond to the resulting electric fields. Under the right conditions, grains may be lifted from the surface and hover or hop above the ground. No wind is required. No air is present to carry them. Electric forces alone may be enough. This idea has fascinated scientists studying the Moon and other airless bodies because it suggests that a surface can appear still while its finest material is quietly mobilized. Imagine a barren landscape under a black sky, with dust rising not in a storm, but in a faint electrostatic dance. It changes how we think about such places. Even without atmosphere or weather in the familiar sense, the surface is not necessarily motionless. Electric fields can make the smallest grains behave as though the world itself were subtly stirring them into suspension. Lunar dust may cling stubbornly to surfaces like abrasive black powder. Moon dust is not soft like household dust, and it is not rounded like sand shaped by wind and water. Because the Moon has no atmosphere and no flowing water, grains there are often jagged and sharp, created by countless impacts that shatter rock without smoothing it. Add electric charging from sunlight and the fine powder can cling stubbornly to suits, tools, seals, and equipment. It behaves less like harmless dust and more like abrasive black powder that wants to follow you everywhere. This matters because anything that clings that well and scratches that easily becomes a serious practical problem. The Moon may look serene from Earth, yet its surface material is harsh and intrusive at close range. It sticks where it is not wanted and grinds where it is not welcome. That contrast is unforgettable. One of the most beautiful objects in the sky is coated in fine dust that behaves like a persistent, abrasive nuisance. Apollo astronauts found moon dust clingy, sharp, and deeply troublesome. The Apollo missions revealed that lunar dust was more than a curiosity. It was a real hazard. Astronauts tracked it into the spacecraft on their suits and boots, where it clung to fabric, scratched surfaces, and got into unexpected places. It smelled strange after exposure to the cabin, and it irritated eyes and airways. Because the grains were sharp and angular, they could wear down seals and abrade equipment. What looked outside like a fine grey powder turned into a stubborn operational problem once humans had to live and work around it. That discovery gave the Moon a new kind of realism. It was not just a silent landscape of craters and light. It was an environment with a difficult surface material that resisted easy handling. Future missions must take that seriously. In a way, the dust changed lunar exploration from a romantic image into an engineering challenge. Even a small grain can become important when it gets everywhere and refuses to leave. Cosmic dust can damage spacecraft despite being almost unimaginably small. A grain of dust sounds harmless until you remember the speeds involved in space. Spacecraft move fast, and so do the particles they encounter. When a tiny grain strikes at those relative velocities, the impact can release surprising energy, enough to pit surfaces, erode delicate materials, or create small clouds of plasma. Over time, repeated hits can wear instruments, degrade optics and threaten exposed components. Engineers design missions with this in mind, especially when sending spacecraft through dusty regions such as comet environments or ring systems. The danger is not that each particle is large. It is that even something microscopic becomes a projectile when the closing speed is extreme. This is one of the most wonderful lessons of cosmic dust. Size alone does not decide importance. A particle too small to see clearly with the naked eye can leave scars on a spacecraft built with extraordinary care. In space, tiny things can become dangerous simply because the universe moves so fast. A tiny grain can strike faster than a rifle bullet. Here on Earth, a rifle bullet already feels astonishingly fast, but many dust grains in space can hit at even greater speeds. Relative velocities between spacecraft and particles can climb to many kilometers per second, far beyond anything most people have ever experienced directly. At those speeds, an almost invisible grain carries enough energy to make a serious impact. It can vaporize part of itself and part of the surface it hits, producing a tiny flash, a crater, or a burst of charged material. The comparison is startling because the grain itself is so small. It has no dramatic appearance, no visible threat, and no sound announcing its approach. Yet in motion, it becomes formidable. This is why mission planners worry about dust and why instruments can sometimes detect impacts as sudden signals rather than as objects seen in advance. A speck of matter at cosmic speed is not just dust anymore. It becomes a hypervelocity event, compressed into an instant. Spacecraft sometimes detect dust by listening for microscopic high-speed impacts. Out in space, a grain of dust can arrive too fast and too small to photograph in any ordinary way, yet a spacecraft can still notice it. When such a particle slams into a detector or even a metal surface, the impact can create a tiny burst of plasma, an electrical pulse, or a sharp mechanical vibration. Instruments are designed to catch those fleeting signals and translate them into evidence that a grain has struck. In a sense, the spacecraft is listening for taps from invisible visitors. This turns dust detection into something almost musical. The cosmos becomes a place of faint knocks, clicks, and pulses, each one announcing a particle that crossed immense distance only to end its journey against a machine made by human hands. It is a beautiful method because it respects the scale of the subject. Cosmic dust is often too small to see directly, so we learn to hear it instead, through the brief signature of impact. Juno recorded dust strikes while traveling from Earth toward Jupiter. As Juno made its long journey outward, it was not traveling through empty silence. Along the way, the spacecraft encountered dust and registered impacts from tiny particles crossing its path. Some detections came through subtle signals caused by grains striking parts of the spacecraft and disturbing its electrical environment. That meant Juno was not only on its way to study Jupiter, it was also sampling the fine material drifting through the solar system between planets. There is something thrilling about that. A mission aimed at a giant world still had stories to gather from the smallest travelers in space. Each strike hinted at the dust population spread along the route, including material connected to collisions and distant activity elsewhere in the solar system. A spacecraft bound for one great target still feels the presence of countless tiny ones. Even on a voyage toward Jupiter, the road itself is made of particles, and some of them leave their signatures as they arrive. Cassini tasted dust around Saturn to learn where it came from. Cassini did not merely look at Saturn's environment. In some cases, it sampled it directly. As the spacecraft moved through the Saturn system, its instruments encountered tiny grains and analyzed their composition, charge, and behavior. This allowed scientists to ask a remarkable question. Was a given particle born in a ring, launched from a moon, or altered by its journey through Saturn's magnetic environment? In effect, Cassini was tasting the dust and reading its history. That phrase sounds poetic, but the science behind it is wonderfully concrete. The chemistry and physical properties of a grain can reveal its origin story. One particle may point back to Enceladus and its icy plumes. Another may carry clues from a ring arc or a more distant, dusty region. Saturn becomes far richer when seen this way. It is not just a planet with rings and moons. It is a whole connected system where fine particles move between worlds and carry memories with them. Stardust returned comet dust to Earth in a tiny capsule. One of the boldest missions in dust science did something almost unbelievable. It flew to a comet, gathered material from its coma, and brought part of that material home. The Stardust mission used special collectors made of aerogel, an ultralight solid so delicate and strange-looking, but it seems almost unreal. When dust grains struck it, they burrowed in and slowed down gradually, instead of shattering completely. Later, a small return capsule carried those captured particles back through Earth's atmosphere for recovery. That means human beings have held comet dust in laboratories, not as distant speculation, but as real material returned from deep space. There is a special intimacy to that achievement. A comet, once visible only as a streak in the sky, became a source of tangible grains that scientists could study one by one. The mission turned a celestial wanderer into something touchable and made ancient dust part of earthly science. That mission captured particles moving faster than a speeding bullet. Collecting comet dust sounds delicate, but the actual encounter was violent. The particles met the Stardust spacecraft at tremendous speed, far faster than a rifle bullet travels through air. At those velocities, even a tiny grain has enough energy to destroy itself or the collector, unless the capture method is extraordinarily clever. That is why aerogel was so important. Instead of letting the particle smash into a hard surface, the collector allowed it to carve a long, narrow track and lose speed more gradually. Even then, some grains were altered or fragmented by the impact. The challenge itself is what makes the mission so fascinating. It was not like scooping up drifting snow. It was more like catching microscopic projectiles fired by a comet across space. And yet it worked. Scientists brought some of those grains home and studied them in detail. The feat was equal parts engineering and audacity, a way of catching bullets made of ancient dust without losing everything in the moment of capture. Some returned grains carried material older than the solar system. Among the particles studied from returned comet material, scientists found signs that some ingredients were astonishingly ancient. Mixed into the comet dust were presolar grains, tiny survivors from stars that existed before our sun formed. These grains had endured not only the death of their parent stars, but also the birth of the solar system and the long, cold storage of cometary ice. Then, after billions of years, they were collected by a spacecraft and delivered to laboratories on Earth. It is hard to overstate how extraordinary that chain of events is. A grain born around another star, older than the Sun, older than Earth, older than every ocean and mountain, ended up inside a capsule built by humans. Comets are so valuable partly because they preserve primitive material with less alteration than planets do. They are deep freeze archives of early history. In some cases, they preserve not just early solar system history, but relics from the era before our system even existed. Scientists collect micrometeorites from rooftops, deserts, and Antarctic snow. Not every valuable sample of cosmic dust comes from a spacecraft mission. Scientists and skilled collectors can find micrometeorites right here on Earth in places where tiny extraterrestrial particles are easier to separate from ordinary dirt. Flat rooftops can gather them over time. Dry deserts preserve them with relatively little chemical alteration. Antarctic snow and ice are especially useful because the background material is so clean and the contrast can be striking. What makes this so captivating is the accessibility of the idea. Space is not only visited by rockets and telescopes. It is quietly delivered to the ground in microscopic form. A researcher can melt snow, sort sediment, or examine rooftop residues and sometimes uncover particles that once traveled through interplanetary space. The method feels almost magical, yet it is real science built on patience, careful identification, and deep knowledge of what distinguishes cosmic grains from earthly ones. The sky leaves tiny gifts behind, and scientists have learned where to look. Your roof may hold real cosmic dust mixed with city grime. It sounds unlikely, almost mischievous, but a flat roof in a busy city may contain genuine particles from space. Over time, micrometeorites settle out of the atmosphere along with soot, pollen, industrial residue, and ordinary dust from the street below. Hidden in that messy mixture can be tiny rounded grains rich in iron-bearing minerals and formed during fiery passage through the atmosphere. The challenge is that city grime is plentiful and cosmic particles are rare by comparison. They do not announce themselves. They hide among the mundane. That is part of the charm. The extraordinary can arrive mixed with the ordinary, unnoticed for years. It means the distance between the cosmos and daily life is smaller than it feels. Above the top floor of an apartment block or office building, among leaves, grit, and urban residue, there may be grains that once orbited the sun before plunging through Earth's air. Even a roof can become a collection point for the universe. Most micrometeorites are smaller than a grain of sand. Many people imagine meteorites as dramatic rocks, heavy and blackened, found in deserts or displayed in museums. Micrometeorites are a different world entirely. Most are tinier than a grain of sand, so small that you could brush them away without ever knowing what they were. Yet each one may have traveled through space for immense lengths of time before meeting Earth. Their small size is part of what makes them so fascinating. They are easy to overlook, but they are also incredibly numerous compared with larger meteorites. Day after day, the planet gathers these minute visitors in a slow, invisible rain. To recognize one requires magnification, patient sorting, and an eye for telltale features. That act of recognition changes your scale of wonder. Suddenly, the cosmic is not only grand and blazing overhead, it also arrives as tiny particles that settle silently onto the ground. The universe does not always visit in spectacular stones. Sometimes it arrives as dust finer than sand. Some melt into tiny spheres as they blaze through air. When certain small particles plunge into Earth's atmosphere, friction and compression heat them so intensely that they melt. Because they are tiny, surface tension can pull the molten material into near spherical shapes before it cools and hardens again. The result is a micrometeorite that looks like a miniature bead forged in flight. These little cosmic spheres are among the clearest signs that a particle endured a fiery atmospheric entry rather than forming on Earth. In a way, they are droplets of a brief catastrophe. A grain that spent ages drifting through space suddenly became a tiny molten object, then froze again before reaching the ground. That transformation is extraordinary. It means some of the smallest particles collected from rooftops or Antarctic ice are shaped not only by their origin in space, but by the violence of arrival. They carry two histories at once, one from the solar system beyond Earth, and one from the blazing seconds when our atmosphere remade them. Others survive entry with delicate structures still astonishingly intact. Not every cosmic grain is melted into a neat sphere during descent. Some enter in ways that are gentler, whether because of their speed, angle, size, or composition, and they preserve remarkably delicate internal textures. Under the microscope, these particles can show fine mineral arrangements, porous frameworks, and primitive structures that would have been lost if the heating had been too severe. That is what makes them so valuable. They can retain clues to the environments where they formed and the history they experienced before reaching Earth. Imagine something fragile enough to be altered by a brief pulse of heat, yet tough enough to survive a fall from space with much of its original character still present. These particles feel almost miraculous. They passed through the atmosphere, the very barrier that destroys so many incoming grains, and still arrived bearing details from deep time. In some cases, the journey from space to Earth preserves not just the object, but the memory of its ancient construction. Antarctic ice preserves cosmic dust like a frozen scientific archive. Antarctica is one of the best places on Earth to search for micrometeorites because the ice acts like a patient collector and preservative. Far from most human pollution and rich in clean frozen surfaces, the region allows extraterrestrial particles to accumulate in a setting where they can later be concentrated and studied. Snow falls, dust settles, layers build, and time does the sorting. In some areas, the movement and sublimation of ice can leave particles enriched at the surface, ready for careful collection. What emerges is almost like a frozen archive of material from space. Each grain is a page in a record that was written above the atmosphere and stored in the cold. There is something deeply satisfying about that image. The most remote ice on Earth quietly gathers evidence from the wider solar system. Long after a particle's fiery entry, Antarctica keeps it still, cold and recoverable, allowing science to read what the sky has been dropping for ages. Deep-sea sediments also hide a slow rain of cosmic particles. The deep ocean floor seems about as far from astronomy as a place can be, yet it too collects material from space. Far below the waves, sediments build up slowly over immense periods of time, trapping tiny extraterrestrial grains among clay, mineral fragments, and the remains of marine life. This makes the seafloor a quiet archive of cosmic infall. The particles that settle there are not dramatic. They arrive one by one in a long, patient drizzle from above. Over thousands and millions of years, that drizzle becomes part of the geological record. Scientists can recover and examine some of these particles, tracing their composition and learning about the constant exchange between Earth and space. The idea has a special beauty to it. A grain can cross the atmosphere, sink through water, and come to rest in darkness on the seabed, where it waits in the mud like a tiny celestial fossil. Even the deep sea bears witness to the sky. Some cosmic dust contains amino-rich compounds linked to prebiotic chemistry. Certain cosmic particles are chemically richer than people expect. In some primitive materials from comets, meteorites, and related dust, scientists have found organic compounds including amino-related molecules that matter deeply in the chemistry of life. These are not living things, and they are not proof that life arrived ready-made from space. What they do show is that some of the ingredients associated with biology can form or survive in extraterrestrial environments. That alone is enough to shift the imagination. A tiny grain drifting through darkness may carry complex carbon chemistry that connects to the prebiotic story of worlds like ours. The important point is possibility. Space is not chemically barren. Even in cold and remote places, compounds can assemble that later become relevant when delivered to a planet with the right conditions. Cosmic dust, then, is not only an archive of stars and collisions. It is also part of a chemical bridge between astronomy and the earliest stages of biology. Dust may have delivered part of life's raw chemistry to Earth. Early Earth was bombarded by material from space far more intensely than it is today, and among that incoming matter would have been dust rich in carbon-bearing compounds and other reactive ingredients. This has led scientists to consider a powerful idea. Perhaps some fraction of the raw chemistry needed for life was delivered, rather than made entirely on the surface. The key word is part. Dust would not have been a finished recipe, but it may have provided useful molecules, extra carbon, and chemically interesting material that joined Earth's own active environment of water, heat, minerals, energy sources. That possibility is thrilling because it makes life's beginnings feel more cosmic without making them less earthly. The young planet may have been both laboratory and recipient, building its own chemistry while accepting contributions from above. If so, every living thing, owes a little something to drifting grains that fell through ancient skies. The boundary between planet and cosmos may have mattered less than we once thought. Carbon-rich grains drift through space, carrying surprisingly complex molecules. Space is often imagined as too harsh and empty for interesting chemistry, yet carbon-rich dust grains prove otherwise. Some of these particles carry surprisingly elaborate organic material, including aromatic compounds and other molecular structures far more complex than bare simple gases. In cold clouds, around dying stars, and in primitive solar system bodies, carbon chemistry can grow richer than intuition suggests. The grain becomes both carrier and environment. It protects certain molecules, exposes them to radiation, and participates in a slow chemical story that unfolds over long periods. What is so captivating here is the contrast. A place that looks black, silent, and hostile can still host molecular complexity on a microscopic scale. A grain drifting between stars may be transporting not just elements, but an entire chemical mood, rich, dark, and full of potential. These particles remind us that complexity does not wait for planets. Some of it is already traveling through space, built into the dust itself. Interstellar dust helps molecules form on its icy surfaces. In the coldest interstellar clouds, atoms and simple molecules do not always react efficiently in the gas alone. Dust changes that. Tiny grains provide surfaces where particles can land, linger, and meet. On these icy coatings, atoms that would otherwise drift apart can settle close enough to react and form new molecules. Hydrogen, the most abundant element, is especially important here. On grain surfaces, it can combine more readily, helping create molecular hydrogen, the basic fuel of many cosmic environments. From there, richer chemistry can follow. Dust, in this sense, is not passive debris. It is a stage on which chemistry becomes easier. The frozen surface of a grain acts almost like a laboratory bench suspended in darkness. That is one of the most wonderful reversals in the topic. Something we call dust sounds inert and insignificant, yet in interstellar clouds, it can become the place where atoms finally meet, join, and begin building a more complicated universe. Even simple water can assemble on the surfaces of dust. Water in space has a story that is far more intimate than many people realize. In deep, cold clouds, some water molecules can form on the surfaces of dust grains, where oxygen and hydrogen-bearing particles meet and react. The grain offers a place for those ingredients to pause, combine, and remain long enough for chemistry to succeed. Over time, water can build up as part of an icy coating around the grain. That means one of the most familiar substances in our lives can begin not in oceans or clouds on a planet, but on tiny particles drifting through interstellar darkness. The image is extraordinary. Somewhere in a frigid cloud between stars, a microscopic grain is gathering frost made partly of newly assembled water molecules. Later, such material can be carried into star-forming regions, disks, comets, and perhaps planets. Dust thus becomes part of the long cosmic route by which water travels from interstellar chemistry to worlds where it can fill seas. Dust grains often wear coats of ice in deep, cold clouds. Far from hot stars, in the coldest and darkest molecular clouds, dust grains can become coated in thin, icy mantles. These are not thick, glistening shells like winter frost on a window, but microscopic layers built molecule by molecule in frigid conditions. Water is common in these coatings, along with other frozen substances that gather from the surrounding gas. Once the ice forms, the grain becomes chemically more interesting and physically altered. It can stick differently, absorb light differently, and host reactions that are difficult in the gas alone. In a sense, the grain puts on a winter coat and enters a new phase of its life. This matters because such icy grains are part of the raw material from which stars, comets, and planets can later form. The cold cloud is not empty gloom. It is full of tiny particles wearing invisible frosts. each one carrying frozen chemistry through darkness, while waiting for the next chapter of cosmic evolution. Those icy mantles can trap carbon monoxide, methanol, and water. Once an icy layer forms on a dust grain, it can act like a tiny freezer for volatile molecules. Carbon monoxide, water, methanol, and other substances can become locked into that mantle under the deep cold conditions of interstellar clouds. This storage matters because it preserves chemistry that can later be released or transformed when the environment changes. If a nearby star begins to warm the region, some of those trapped molecules can evaporate back into the gas or take part in new reactions. So the grain is not just carrying ice, it is carrying the frozen inventory of ingredients gathered in darkness. That makes each icy particle a little archive of cold cloud chemistry. When astronomers study such environments, they are reading the behavior of countless microscopic freezers suspended between stars. What seems like a simple coat of frost is actually a rich reservoir of molecules waiting for heat, light, or time to unlock the next step in the story. When stars warm the ice, hidden chemistry can suddenly awaken. In the deep cold between stars, icy dust grains can sit unchanged for ages, holding frozen molecules in silence. Then, a nearby star begins to form, and everything changes. As the region warms, those icy mantles start to soften, rearrange, and release their contents. Molecules that were trapped in the frost can move, meet new partners, and take part in fresh reactions. Others evaporate back into the gas, filling the cloud with compounds that were hidden moments before on a cosmic timescale. It is a little like opening countless sealed jars at once inside a stellar nursery. Suddenly, the chemistry of the entire region becomes richer and more active. This matters because young stars do not form in empty space. They inherit matter that has already been processed, stored, and then unlocked by heat. Dust grains spend ages gathering ingredients in darkness, and when the warmth arrives, they help turn a frozen archive into a living chemical environment. Dust is one of the universe's quietest chemical laboratories. A laboratory usually sounds busy in the mind, full of glassware, heat, sparks, and human hands. Cosmic dust does its chemistry in almost complete silence. A grain drifts through a cold cloud, gathers a thin, icy coating, and offers a surface where atoms can pause long enough to react. Over time, simple ingredients can combine into more interesting molecules, not through grand explosions, but through patience. That is what makes dust so extraordinary. It turns empty-looking regions of space into places where chemistry can keep advancing even in darkness. Each grain is tiny, yet the number of grains is immense, and together they create a distributed laboratory spread across whole clouds between stars. No walls, no benches, no instruments, and still, the work goes on. The result is that space becomes chemically inventive long before planets ever appear. Dust does not merely survive the universe. It helps it experiment, one microscopic surface at a time. Some grains were forged in red giants nearing the ends of life. Not every dust grain begins in a violent explosion. Some are born in the slow, swollen atmospheres of red giant stars approaching the final chapters of their lives. These stars expand enormously as they age, and their outer layers cool enough for atoms to condense into solid particles. Deep inside the star, new elements have been forged through nuclear burning. In the extended outer envelope, some of that enriched material can finally gather into microscopic grains and then drift outward on stellar winds. The process is strangely gentle for something so grand. A giant star that once shone steadily for ages begins to lose itself, breath by breath, and in that outflow dust is born. Those particles then enter the wider galaxy and may later become part of clouds, comets, meteorites, or planets. A dust grain from a red giant is a fragment of stellar old age made solid. It is matter released not in fury, but in a long, luminous farewell. Others were blasted outward by supernova and scattered across space. Some dust grains have a far more violent origin. When a massive star reaches the end of its life, it can explode as a supernova, blasting newly forged elements into space with astonishing force. In the expanding debris, as temperatures fall, some atoms condense into solid particles. These grains are born in one of the most extreme environments in the universe, surrounded by shock waves, intense radiation, and expanding gas moving at immense speeds. It is remarkable that any solid material can form there at all. More remarkable still is that some survives the chaos and escapes into interstellar space. A supernova does not just destroy. It also enriches the galaxy, seeding it with heavy elements and dust that may later become part of entirely new stars and planets. In that sense, these grains are born from catastrophe and carried forward as future ingredients. A supernova dust particle is both a remnant of death and a contribution to what comes next. Presolar grains carry isotopic fingerprints from stars long since gone. Some grains preserve ratios of isotopes so unusual that they stand apart from the ordinary material of the solar system. These ratios act like fingerprints because different kinds of stars make different patterns of isotopes as they age and die. When scientists find a grain with one of these strange signatures, they know it did not form here. It was inherited from an earlier stellar environment and preserved through deep time. That discovery is one of the great triumphs of laboratory cosmochemistry. A particle almost too small to see can reveal the identity of a vanished star through the exact mix of atoms locked inside it. The star itself is gone. Its light faded long before Earth existed. Yet the grain remains, carrying a record that no telescope could have captured directly. In this way, presolar dust becomes personal evidence of ancient stellar lives. The galaxy leaves signatures in its dust, and some of those signatures survive long enough for us to read them. Each such grain is like a message from one vanished star. There is something almost intimate about holding a grain that formed around a star that no longer exists. The star is gone, its outer layers dispersed, its light long extinguished in the local sky, yet one tiny particle from that lost environment survives. In a strict scientific sense, the grain is a chemical record. In a human sense, it feels like a message. It carries evidence of temperature, composition, and stellar processes from a place that can never be visited again. We cannot watch that specific star evolve. We cannot rewind the galaxy and see it shed the grain. But the grain itself remains as testimony. That is what gives cosmic dust such emotional force. It is not only matter, it is surviving context. A vanished star can still be known through something microscopic that endured the destruction of one world and the creation of another. A message does not have to be written in words. Sometimes it is written in atoms and lasts for billions of years. Scientists can identify a grain's stellar birthplace from its atoms. The remarkable part of this science is not just that ancient grains survive. It is that scientists can often trace them back to the kind of star that made them. They do this by measuring isotopes and elemental abundances with extraordinary precision. Different stellar environments leave different chemical signatures. A grain from a red giant may show one pattern. A grain formed in a supernova may show another, richer in certain isotopes created in explosive nuclear processes. These signatures are so distinctive that a microscopic particle becomes something like a passport, stamped by its place of origin. That ability changes the nature of astronomy. Usually we study distant stars through light alone. With presolar grains, we can examine actual material from ancient stellar sources in the laboratory. That is an astonishing shift in scale and intimacy. The grain becomes a physical sample from a stellar birthplace far older than our planet, and the atoms inside it preserve enough evidence for science to reconstruct where it first came into being. That makes cosmic dust one of astronomy's tiniest historical records. History is usually imagined in grand things, Ruins, fossils, mountain layers, old manuscripts. Cosmic dust asks us to think smaller. A single grain can preserve a sequence of events that begins around a long dead star, passes through interstellar space, survives incorporation into the young solar system, and ends in a meteorite or laboratory on Tian. Earth. Few objects record such an enormous span of time in such a small form. That is why dust deserves to be thought of as a historical record, not merely a scientific sample. It carries chronology, origin, and transformation inside itself. Its structure and chemistry are the record. The dates are written in isotopes. The places are marked by elemental patterns. When scientists decode that information, they are not just measuring matter. They are reading a history older than Earth. It is wonderful to realize that the universe keeps archives in microscopic form. One of astronomy's most delicate records is not stored in light alone, but in dust grains you could never notice by A. Dust from dying stars helps seed the next generation of suns. When stars age and shed material, or die in more dramatic ways, they do not simply vanish into meaninglessness. They return enriched matter to the galaxy, and part of that return comes in the form of dust. Those grains mix into larger clouds of gas and particles that drift through interstellar space. Over time, some of those clouds collapse under gravity and form entirely new stars. That means the dust from one stellar generation can become part of the raw material for the next. In a very real sense, the galaxy recycles through dust. Old stars enrich the medium, and future stars inherit that enrichment when they are born. This is one of the most beautiful cycles in astronomy. The end of one star can quietly contribute to the beginning of another. Dust makes that inheritance tangible. It is not an abstract idea about matter being reused. It is actual solid material, forged in stellar endings, then folded into the clouds from which new suns eventually ignite. In that sense, cosmic dust is matter, learning to begin again. A dust grain can seem like the end state of something larger, the residue after fire, collision, or erosion. Yet in cosmic history, dust often acts more like a beginning than an ending. Material leaves a dying star, cools into grains, drifts through space, joins a cloud, becomes part of a new stellar nursery, and later finds its way into disks, comets, moons, or planets. The same matter keeps entering new stories. That is why dust feels so profound. It is not static debris. It is a traveler between generations of structure. A grain may begin in the atmosphere of one star and finish in the crust of a world that forms billions of years later. In that journey, matter does not merely persist. It becomes available again for new roles. Seen this way, cosmic dust is one of the universe's great instruments of renewal. It carries the past forward, not as a museum piece, but as something ready to take part in creation once more. Dust can polarize light, revealing invisible magnetic fields in space. Magnetic fields in space are difficult to see directly, yet dust provides a subtle way to trace them. Many grains are not perfect little spheres. They can be elongated, and under certain conditions they tend to align with magnetic fields. When light passes through or is emitted by clouds full of such aligned grains, the light becomes polarized. That means its waves are no longer oriented in random directions. Astronomers can measure that polarization and use it to infer the structure of magnetic fields threading through dusty regions. It is an elegant piece of detective work. The field itself remains invisible, but the dust responds to it and leaves a clue in the light. This matters especially in star-forming clouds, where magnetic structure can influence how gas moves and collapses. Dust becomes a translator between hidden forces and visible evidence. A grain smaller than smoke can help map magnetism across enormous reaches of space simply by changing the orientation of light. By tracing dusty light, astronomers map structures they cannot touch. Astronomy often depends on reading light from a distance, and dust adds extra layers of information to that reading. By studying how dusty regions absorb, emit, and polarize light, astronomers can reconstruct shapes, flows, and hidden structures inside places no probe can reach. A cloud may look featureless at first glance, but dusty emission can reveal filaments, arcs, knots, and boundaries that tell a far richer story. Polarization can hint at magnetic directions. Infrared glow can show where material is warmer or denser. Extinction maps can reveal where starlight is being blocked most strongly. None of this involves touching the cloud itself. The structure is inferred from the behavior of light passing through or emerging from dust. That is what makes the method feel so powerful. Astronomers can sketch the architecture of remote regions using only the clues left in dusty light. The universe hides behind distance, but dust gives back enough evidence for us to map places our hands will never reach. Dust helps sculpt the grand spiral arms of many galaxies. Spiral arms are not just gatherings of stars. They are also regions where gas and dust concentrate, compress, and respond to the large-scale dynamics of a galaxy. Dust helps make these arms visually dramatic by tracing lanes of dense material and by participating in the clouds where star formation becomes active. As gas flows through a spiral pattern, it can be compressed, and dust comes with it, helping mark the places where new stars are likely to emerge. The arms thus become not only bright stellar features, but structured environments rich in fine particles and cold material. This gives many galaxies their layered look, with glowing star-forming regions, dark lanes, and sweeping curves. Dust is not the only thing shaping an arm, but it is one of the ingredients that makes the structure vivid and physically important. When we admire the graceful sweep of a spiral galaxy, part of what we are seeing is dust helping to define where matter gathers and where future stars will appear. Giant dust lanes can divide galaxies with dramatic bands of darkness. Some galaxies are crossed by dark bands so striking that they seem almost painted on. These are giant dust lanes, and they can cut across bright stellar backgrounds with astonishing contrast. In edge on spiral galaxies, the effect can be especially dramatic. A glowing disk of stars is split by a thick central lane of darkness where dust blocks the light behind it. The result is one of the most beautiful and unsettling sights in astronomy. A galaxy can look both radiant and wounded at the same time, with shadow running through its brightest regions. Yet the darkness is not empty. It is dense material, full of gas and particles that may later help form more stars. Dust turns absence into structure again. Instead of a simple glowing swarm, the galaxy becomes layered and dimensional. One dark lane can reveal where matter is concentrated and where light is being held back. A shadow across a galaxy is often the signature of hidden richness, not missing substance. Some galaxies are so dusty they hide furious star formation within. There are galaxies that appear modest or even obscured in visible light, yet inside them stars are being born at extraordinary rates. Dust is the reason they can seem so deceptive. Large amounts of it absorb the fierce radiation from stellar nurseries and re-radiate that energy at infrared wavelengths. To human eyes or ordinary optical telescopes, much of the action is hidden. To infrared observatories, those same galaxies can blaze. This creates a wonderful reversal. The dust conceals the very thing it is helping us identify. Astronomers know that some of the most productive star-forming galaxies in the universe are dusty systems whose true activity becomes clear only when viewed in the right wavelengths. Inside these galaxies, gas is collapsing, young stars are igniting, and energy is pouring out, all partly veiled by particulate matter. Dust does not mean inactivity. Sometimes it means the opposite. A galaxy wrapped in dust may be one of the busiest stellar factories in the cosmos. The brightest infant stars often grow in places optical telescopes cannot see. The earliest stages of stellar growth are often hidden deep inside thick clouds where visible light cannot escape easily. That means some of the brightest and most energetic young stars are effectively invisible to ordinary optical telescopes while they are still embedded in their birth environments. They may be blazing in infrared, heating surrounding dust and driving jets into the cloud, yet remain concealed behind veils of obscuring material. This makes stellar youth feel wonderfully secretive. The brightest beginnings do not always announce themselves with clear, visible light. Sometimes they happen behind curtains of dust, and only specialized observations can reveal them. That fact reshapes our intuition about brightness and visibility. A source can be intensely luminous and still hidden from the most familiar kind of view. Dust forces astronomy to become more imaginative, because what matters is not only how much energy a star releases, but how that energy travels through the material around it before it reaches us. Dust can both conceal the universe and help explain it. At first, dust seems like an annoyance to astronomers because it blocks light, hides stars, and complicates observations. Yet the more closely you look, the more it becomes clear that dust is also one of the best guides to what is happening in the cosmos. It conceals, yes, but the very way it conceals carries information. It tells us where matter is dense, where stars are forming, where light is being absorbed and reprocessed, and how energy moves through galaxies and clouds. Dust also emits its own radiation, allowing hidden regions to be mapped in other wavelengths. So it does not merely get in the way of understanding. It becomes part of the explanation. This double role is one of the reasons the subject is so captivating. The same material that frustrates a simple view of the universe also makes a deeper view possible. Dust is both veil and clue, both obstacle and evidence, both hiding place and teacher. Without accounting for dust, galaxies can look younger or older. Dust changes the light that reaches us from galaxies, and if astronomers ignore that effect, they can misread the story of an entire system. A dusty galaxy may appear redder, dimmer, or differently balanced in its starlight than it truly is. That can affect estimates of age, star formation activity, and the relative contributions of young and old stars. In some cases, dust can hide vigorous stellar birth and make a galaxy seem quieter or more evolved than it really is. In other cases, complicated mixtures of dust and starlight can distort the interpretation in subtler ways. This is why careful models of galaxies must include dust, not as decoration, but as a major actor in how the light is shaped before it arrives. It is extraordinary that a galaxy containing hundreds of billions of stars can be misread because of fine particulate matter drifting among them. Dust influences not only what galaxies are, but how old or young they appear to be. Dust changes color too, reddening starlight that passes through it. When starlight passes through dusty space, the change is not only a reduction in brightness, the color shifts as well. Dust grains are generally more effective at scattering and absorbing shorter wavelengths of visible light, especially blue light, than longer, redder wavelengths. As a result, the light that emerges can look redder than it did when it left the star. This effect, called reddening, can make the universe look warmer in color than it truly is. It is one of the reasons distant stars and galaxies must be interpreted with care. Dust is quietly editing the palette of the cosmos. That is a lovely and subtle power. A cloud between us and a star can tint the light without changing the star itself. The source remains what it is, but the journey alters the appearance. Dust becomes a kind of cosmic filter, softening and reddening the colors of the sky in ways that scientists must carefully measure to understand the truth behind the view. That cosmic reddening can make distant stars seem cooler than they are. Because dust preferentially removes bluer light, a distant star seen through dusty space can look redder and therefore cooler than it really is. If that effect is not corrected, astronomers may misjudge the star's temperature, intrinsic brightness, or even its stage of life. This is one of the great interpretive challenges in observational astronomy. The color that reaches the telescope is not always the color the star truly emitted. It has been modified by the journey. Dust acts like an intervening screen, shifting the apparent character of the source. The result is a useful warning about appearances in the universe. A star may seem calm and cool, simply because dust has filtered out part of its bluer light. Understanding the distortion allows astronomers to reconstruct what the star was actually like before the beam crossed the dusty medium. In that sense, reddening is not only a problem. It is also a clue that tells us something important about the material lying between us and the distant star. Entire maps of the sky must correct for foreground dust. When astronomers try to map the universe, they first have to account for a local inconvenience that is anything but small. Dust in and around our own galaxy lies between us and much of the sky, dimming and reddening whatever sits beyond it. If that foreground veil is not measured and corrected, stars can seem fainter than they are, distant galaxies can look altered, and even the large-scale structure of the sky can be misread. So before many maps are trusted, astronomers build dust maps of the Milky Way itself, tracing where the foreground is thickest and where it thins out. In a sense, they must clean the window before describing the landscape beyond it. That idea is wonderfully humbling. Even when we try to chart the far reaches of the cosmos, our own dusty surroundings leave fingerprints on the view. To see the deep universe clearly, we first have to understand the haze drifting close to home. Some dust grains are elongated, not neat little cosmic spheres. It is tempting to imagine cosmic dust as tiny, perfect beads, simple little spheres floating through space. Many grains are nothing like that. Some are stretched, jagged, or irregular, more like splinters and slivers than smooth pellets. That odd geometry matters. Shape changes how a grain spins, how it lines up with magnetic fields, how it interacts with light, and even how it sticks to other grains in crowded environments. A long, thin particle does not behave quite like a compact one. It presents different surfaces, catches radiation differently, and can tumble through space with its own peculiar rhythm. This gives dust a more vivid physical reality. These are not generic points of matter. They are tiny objects with form, asymmetry, and consequence. A particle with an elongated shape may help polarize light or reveal hidden magnetism in a cloud. In astronomy, even the silhouette of a grain can matter. The smallest details can scale upward into a cosmic effect. Their shapes affect how they absorb, emit, and scatter light. A dust grain does not need to be large to influence light in complicated ways. Its shape alone can change the whole interaction. An irregular or elongated grain may absorb certain wavelengths more efficiently, emit heat differently, or scatter incoming light in preferred directions rather than evenly. This helps explain why dust can tint starlight, create polarization, and produce different signatures at different wavelengths. Light is not simply hitting a generic obstacle. It is meeting an object with geometry. The result is that astronomy becomes more subtle. To understand what dusty regions are doing, scientists must think about the forms of grains, not just their chemical makeup. A long grain and a rounder one can leave different marks on the same beam of light. That is part of what makes cosmic dust so satisfying as a subject. It connects the microscopic and the magnificent. The curve or edge of a particle too small to see can shape the appearance of clouds, galaxies, and the sky itself. Dust can gather into fluffy clusters rather than compact grains. Not every grain travels through space as a tidy, solid little particle. Some join together into loose, porous aggregates that are more like cosmic fluff than compact rock. These clusters can be built from many smaller pieces sticking delicately together, leaving empty space throughout the structure. That makes them lighter for their size, easier to disrupt, and often better at sticking to other particles during the earliest stages of growth in disks and clouds. In some ways, fluff is useful. A porous aggregate has a large surface area and can interact with gas and radiation differently than a dense grain of the same mass. This matters in planet formation, because the first climb from dust to larger bodies may be helped by particles that collide softly and remain attached instead of rebounding apart. The image is lovely. Before worlds become hard and solid, some of their ingredients may pass through a fragile, fluffy stage, like tiny cosmic snow clumps drifting through the nursery of a future planetary system. Some grains resemble soot, while others resemble tiny mineral shards. Cosmic dust is not one uniform substance with one uniform appearance. Some grains are rich in carbon and can look, in their chemistry and behavior, more like soot than stone. Others are silicate-based and resemble microscopic mineral fragments, sharper and more glassy in character. This diversity matters because different grains come from different origins and play different roles in space. Carbon-rich particles may absorb light strongly and contribute to dark, smoky-looking material in certain environments. Silicate grains can show distinct spectral signatures and help reveal the mineral side of dusty clouds and disks. The universe, then, is not filled with one kind of dust, but with a varied population whose members carry different histories. A grain may trace back to a stellar wind rich in carbon, or to a mineral condensation in another setting entirely. That variety makes dust feel less like background and more like cast members in a story. Each type brings its own texture, chemistry, and origin. Interstellar dust is only a small fraction of space, yet powerful. By mass, dust is only a modest fraction of the material in the interstellar medium. Gas dominates the numbers, yet dust punches far above its weight. Those tiny grains block light, reshape thermal balance, host chemical reactions, influence cloud cooling, and help determine where stars and planets can form. That is one of the great lessons of astronomy. Importance is not always tied to abundance. A relatively small ingredient can alter the behavior of an entire environment if it sits at the right crossroads of physics and chemistry. Interstellar dust does exactly that. It affects radiation, chemistry, temperature, and visibility all at once. Remove it from the galaxy, and much of what we recognize about star-forming clouds, dark lanes, reddened starlight, and molecular richness would change dramatically. Dust is a minority component with major consequences. It is a quiet force multiplier in space, proving that the smallest fraction of a scene can still help determine how the whole drama unfolds. A little dust can profoundly change how a whole cloud behaves. Imagine a giant cloud in space, cold, dark, and spread across trillions of kilometers. Add only a modest amount of dust, and suddenly the cloud handles light, heat, and chemistry very differently. The grains absorb and scatter radiation, give molecules surfaces on which to form, and help the cloud cool by re-radiating energy. That cooling can make gravity more effective. The added chemistry can enrich the environment. The altered light can hide or reveal different regions depending on the wavelength used to observe it. So even a little dust can change the fate of a whole cloud. It can help decide whether the cloud remains diffuse, fragments into denser knots, or begins the long process towards star birth. That is the scale of its influence. Fine particles, present in modest proportion, can steer the behavior of structures vastly larger than any solar system. Dust does not merely decorate a cloud. It can help govern the cloud's future, from its temperature to its hidden chemistry. Dust helped turn a young solar system from chaos into structure. The early solar system was not born orderly. It began as a turbulent disk full of gas, drifting solids, collisions, gradients, and restless motion around a young sun. Dust was central to turning that confusion into architecture. Tiny particles absorbed heat, condensed from hot material or survived from earlier eras, settled through the disk and began to gather into larger clumps. Different regions sorted materials differently. Some solids drifted inward. Others remained farther out where ices could survive. Over time, what would be the broad, messy disk developed rings, concentrations, and the first solid pathways toward planetesimals and worlds. Dust was the bridge from raw disorder to recognizable structure. Without it, there would be no rocky building blocks, no pebbles, no embryonic planets, no meteoritic leftovers preserving early history. The remarkable thing is how humble the beginning was. The solar system that now contains planets, moons, and belts of debris first moved toward order through the behavior of tiny drifting grains. Many meteorites still contain ancient dust trapped inside stone. A meteorite may look like solid rock, but inside some of them are tiny preserved grains that tell a story far older than the stone's arrival on Earth. Certain primitive meteorites formed from material that changed very little since the early solar system, and within that material, ancient dust can remain locked in place like fossils in mineral form. Some grains are presolar. Others are among the earliest solids formed around the young sun. All of them turn an ordinary-looking fragment of space rock into a time capsule. When scientists dissolve away surrounding material or examine thin sections under powerful instruments, they can uncover these microscopic survivors and read histories written long before Earth had continents or oceans. That is part of the wonder of meteorites. They are not just stones that fell from the sky. Some are vaults. Hidden within them are particles that escaped melting, mixing, and destruction, and waited for billions of years inside rock before finally being recognized for what they are. Those grains are among the oldest solids humans have ever touched. Human hands have touched objects from deep antiquity: fossils, amber, ancient tools, ice from old glaciers. Yet some of the oldest solid material ever physically handled by people is measured not in monuments or bones, but in dust grains, isolated from meteorites. Certain presolar particles and early solar system solids formed before Earth existed, before the planets were assembled, and before the surface conditions that would later support life had begun. When scientists separate and study them, they are working with matter that predates every mountain, every ocean basin, and every living lineage on this world. It is almost hard to absorb that fact. A grain invisible without magnification may be older than any rock formed on Earth's current surface. To touch such material, even indirectly in a laboratory, is to reach across almost the full age of the solar system. These are not just old things. They are among the oldest intact solids our species has ever brought into conscious understanding. Cosmic dust falls so gently, but we rarely notice its arrival. For all its cosmic importance, much of this material reaches Earth with almost no drama at all. The tiniest grains do not thunder, blaze brilliantly, or shake the ground. They settle invisibly through the atmosphere, joining snow, rain-washed surfaces, rooftops, and oceans without ceremony. That gentle arrival is part of the subject's strange beauty. Something born in a stellar wind or released by a comet can cross enormous reaches of space and end its journey not with spectacle, but with silence. We are used to thinking the universe announces itself in explosions, eclipses, and fireballs. Dust reminds us that the cosmos also arrives softly. It can drift onto the planet in forms too small for the eye to notice, accumulating over time in places no one would think to call astronomical. The arrival is real, even when it is unseen. Earth is being visited by material from space in a way so quiet that daily life barely registers the contact. Yet over ages, that gentle rain becomes a planetary story. A single grain settling unnoticed onto Earth may seem trivial, but geology teaches patience. When a process continues for immense spans of time, even a gentle rain becomes part of the planet's larger narrative. Cosmic dust has accumulated across oceans, ice sheets, soils, and sediments for billions of years. It has mingled with Earth's own material, contributed extraterrestrial particles to surface environments, and written a faint but persistent connection between this world and the wider solar system. In certain layers and archives, that slow input becomes measurable and meaningful. The story is not one of sudden transformation, but of constant contact. Earth is not sealed off beneath a perfect dome. It is open to a drizzle of material from beyond itself, and over ages the drizzle enters the history of the atmosphere, the oceans, and the crust. The grandeur lies in the timescale. Dust that arrives too quietly to notice in a day can still become part of what shapes a planet across epochs. Dust storms exist in space too, though they follow stranger rules. A storm in space is not driven by wind in the ordinary sense, because there is no dense atmosphere to carry the particles as Earth's air does. Yet dust can still gather, stream, and be rearranged in ways that feel storm-like under stranger rules. Radiation pressure, gravity, plasma effects, collisions, and orbital dynamics can all herd particles into broad structures, flows, and changing patterns. Around comets, dust pours outward in expanding plumes and tails. In disks around stars, grains can concentrate into arcs, rings, and clumps. Near airless worlds, electric fields may loft fine particles above the surface. These are not storms you could stand in, yet they share something with the idea. Dust is mobilized, sorted, and driven into collective behavior by the forces of its environment. The result is a kind of cosmic weather, built not from air and clouds, but from light, charge, gravity, and motion. Space has dust storms, but they answer to a more exotic set of winds. Around some stars, dusty debris disks hint at violent ongoing collisions. Not every dusty disk is a birthplace for planets. Around some mature stars, astronomers find debris disks made from the wreckage of smaller bodies colliding and grinding themselves down. These disks are not primordial leftovers in a quiet state. They are signs that impacts are still happening, perhaps among asteroids, comet-like bodies, or larger fragments left over from planet formation. The dust seen in such disks must often be replenished, because radiation and other processes would otherwise remove it over time. That means something is still breaking apart out there. A bright dusty belt around a distant star can therefore be evidence of violence in progress, a system where collisions continue to generate fine material. The sight is both beautiful and unsettling. What looks like a soft halo may actually be the aftermath of countless impacts. Dust becomes a clue that distant planetary systems are not always settled and serene. Some are still busy shattering small worlds into fresh drifting powder. Those disks can look like celestial construction sites frozen in light. When astronomers image dusty disks around other stars, the view can feel strangely familiar, like seeing a worksite paused in the middle of a giant project. Rings, belts, asymmetries, and gaps suggest that matter is being sorted, moved, or reshaped. In some systems, the dust is part of an early building phase. In others, it is the rubble left by collisions in a system already partly built. Either way, the image feels active. It suggests a place where material has not yet settled into final quiet. That is why the construction site analogy works so well. You can almost imagine scaffolding, traffic, and unfinished architecture, except the tools are gravity, collisions, and light. Dust makes these distant systems legible as places in process. The scene is frozen only because our lives are short. Given enough time, the belts would shift, grains would vanish and be replaced, and worlds might emerge or be eroded. Dust lets us glimpse planetary systems mid-story. Even black holes live in galaxies shaped partly by dust. Black holes may seem far removed from something as humble as dust, yet they inhabit galaxies whose appearance and evolution are influenced by fine particulate matter. Dust helps govern star formation, obscures galactic centers, reprocesses radiation, and shapes how matter is seen as it moves through a galaxy. In active galaxies, Dusty structures near the central regions can even help determine whether the black hole's energetic surroundings appear exposed or hidden from our particular viewpoint. That means dust affects not only the broad look of the host galaxy, but also how one of the most extreme objects in the universe is observed. There is something wonderfully unbalanced about that relationship. A supermassive black hole can outweigh millions or billions of suns, and still the interpretation of its galactic environment is influenced by microscopic grains drifting in surrounding space. Dust and black holes occupy opposite ends of the scale, yet in astronomy they remain connected. Even the most powerful cosmic engines live inside dusty contexts. Dust can survive brutal space, then vanish near intense radiation. One of the marvels of cosmic dust is its toughness. Grains can endure ejection from stars, long drifts through interstellar space, collisions, shocks, and incorporation into clouds or disks. Yet that survival has limits. Move the same grain too close to intense radiation or extreme heat, and it may be altered, eroded, or destroyed entirely. Near hot stars, active galactic centers, or violent energetic environments, dust can sublimate and disappear back into gas. This gives grains a dramatic life cycle. They can survive astonishing ordeals, only to vanish when they cross the wrong thermal boundary. The contrast is striking. A particle may drift for ages through cold darkness and outlast entire worlds, yet fail quickly in the glare of a sufficiently harsh source. That rise and fall is part of the larger dust story. These grains are durable, but not eternal. Their presence marks where conditions allow solids to exist, and their absence marks where radiation becomes too fierce for dust to remain dust. In one grain of cosmic dust, chemistry, history, and astronomy meet. Few objects unite so many sciences in something so small. A single grain can be chemically rich, physically complex, historically ancient, and astronomically significant all at once. Its atoms may record a stellar origin. Its surface may have helped molecules form. Its journey may connect dying stars, interstellar clouds, meteorites, and planets. Study the grain closely enough and you move between chemistry, mineralogy, astrophysics, and planetary science without ever leaving the same microscopic object. That is what gives cosmic dust such unusual power as a subject. It turns vast ideas into tangible things. Instead of speaking only in abstractions about stellar evolution or planetary birth, we can point to a grain and say that the story passes through here. This particle mattered to light, to chemistry, to clouds, to worlds. It is hard to think of another object so tiny that can carry so much meaning. In one grain, the universe becomes local, material, and astonishingly personal. To study cosmic dust is to study how worlds begin. If you follow dust carefully enough, it leads you toward one of astronomy's deepest questions: how scattered matter becomes organized into planetary systems. Dust is there at the start, drifting through interstellar clouds, entering stellar nurseries, settling into disks around young stars, and taking the first fragile steps toward pebbles, planetesimals, and worlds. It also preserves records of the conditions under which those steps happened. In that sense, dust is both participant and witness. It helps build the planets, and it keeps evidence of the building process. That is why the subject feels larger than its name suggests. This is not merely a story about fine debris. It is a story about beginnings, about how something as grand as a world can emerge from particles so small they can barely be seen. When we study cosmic dust, we are studying the earliest chapter of planetary history. We are looking at the material from which moons, comets, asteroids, and habitable worlds first rose. The universe is full of dust, and dust is full of history. By the end of the story, what seemed ordinary becomes almost impossible to call ordinary again. Dust is everywhere, between stars, around planets, in meteorites, in galactic lanes, in comet tails, and falling quietly through Earth's atmosphere. Yet it is never just dust in the everyday sense. Each grain may carry a history of formation, travel, alteration, and survival. Some remember dying stars. Some remember cold clouds. Some helped build planets. Some still drift between worlds. That is why the subject keeps opening outward no matter how small the object becomes. The closer you look, the more history appears. A grain can hold evidence of chemistry in frozen darkness, of stellar furnaces, of ancient collisions, and of the long chain that connects cosmic matter to living worlds. The universe is full of these particles, and that means it is full of tiny archives. Dust is not the leftover part of creation. It is one of the places where creation remembers itself. We've wandered a long way tonight, through one of the smallest and strangest wonders in the universe. We followed cosmic dust from ancient stars to newborn worlds. We watched it drift through dark clouds between the stars, gather in shining disks around young suns, and help shape moons, comets, asteroids, and planets. We traced it through meteor showers, comet tails, Saturn's rings, and the fine invisible rain that still falls on Earth. And somehow, the deeper we went, the more extraordinary it became. What first sounded like something small and forgettable turned out to be full of memory. Tiny grains carried the remains of dead stars. They hid stellar nurseries, helped chemistry awaken in frozen clouds, and preserved some of the oldest material humans have ever studied. Even now, as the night settles around you, there is dust moving through space, dust crossing the atmosphere, dust resting in ice, stone, and sea, each grain holding part of a story far older than our world. So as your thoughts begin to slow, perhaps you can let that image stay with you for a moment. A dark and endless universe, softly filled with drifting particles. Ancient, weightless, and unhurried. Tiny sparks of history moving through starlight. And if this journey helped you unwind, consider liking, subscribing, or leaving a thought below. It helps more wandering minds find their way here. And if you happen to still be awake, there will be another video waiting for you on the screen, ready to carry you a little farther into the night. But for now, there is nothing more you need to do. Let your jaw unclench. Let your shoulders sink. Let your breathing grow slower and softer. And let the last of the day drift away, like dust in the dark between the stars. Sleep well, and good night.